Hey creators, welcome to the Junction Design course, and what we're talking about is the turning radius design methodology. By the end of this lesson, you will be able to draw these turning path movements with proficiency, and you will have a very good understanding of why we have to first understand how these turning path movements are drawn. Now you may be wondering what's the importance of the turning radius design methodology. Now when we are designing junctions, it's quite very essential to ensure that the junctions we design are cater for sufficient and efficient turning movements. Start to finish. So, what's curb to curb and wall turning radius? What are they? Curb to curb turning radius is the minimum radius needed to turn the outer wheel. Now, the wall to wall radius is basically the curb to curb radius, including the overhang. And the inside turning radius is the minimum radius needed to turn the inner wheel. Now, if you look on the right hand side, we have a diagram that's trying to distinguish between the wall to wall turning radius, the curb to curb turning radius, and the inside turning radius. Now, when we are designing most of these vehicles, these turning movements, we are mainly interested in, we start with the curb to curb, the wall to wall turning radius, and then we try to recreate the inside turning radius. That's the goal, and that's what you saw in the earlier simulation. So some fun facts. One, did you know that the car with the smallest turning radius is a Smart Photo 2016? It has a turning radius of 6.9 meters. Then two is the typical turning radius of a car is 10.4 to 10.7 meters. So you find that most situations people tend to flare their junctions by 10 meters or 15 meters. Basically, it's something that's as a result of this. So you may ask yourself, okay, so I know something about the wall-to-wall turning radius. I know something about the curb-to-curb turning radius. How can we reduce or increase this turning radius? So first of all, there's something we look at called the wheelbase. The wheelbase is the distance from the middle of one wheel to the middle of the other wheel. And if you reduce this, you have a much smaller turning radius. Now, if you watch the Mercedes-Benz 2021 promo, there's something they showed in regards to the reduction of the turning circle by 2 meters. And it got me thinking, wow, what have they done to reduce this turning radius by 2 meters in their new Mercedes-Benz S-Class model? So one, you can also modify the front wheels to turn fast, normally faster than normal for drifting cars. And you find that as a result of turning the front wheels faster, you can be able to take a much tighter radius. When we're looking at turning movements and design vehicles at intersections, a number of things happen. How do you look at the vehicle moving from one lane to another? Now, there are different ways. The first is what you're looking at on the top left, where we are having, we drive on the left-hand side. So bear with me. If you drive on the right-hand side, it's still okay. So you come from the inner lane and you merge into the outer lane. That's the outer lane. So you have simulations whereby one is the car comes from the inner lane, the turning car, and merges onto the outer lane. Well, you have cases where you have 2 lanes. Then you have another case where you come from the inner lane and then you're merging, but you are crisscrossing. You first of all try as much as possible to use the maximum sufficient turning movement into the inner lane. Then finally, you have situations whereby you come from the inner lane and then you make the whole turning movement using up both lanes. This is for single lane junctions, and then you come back into the lane that you're supposed to, and you find that this is where normally the stop line is. The stop line is put in places where the turning radius does not affect the cars that are waiting in the opposite lane. So there are a number of ways in which one has to look at these turning movements. So you have to understand, before you design the junction, what's the design vehicle you're looking at, and what kind of maneuvers are you going to look at. Sometimes you don't have the area to acquire more land to try and have these turning movements. So design vehicles we'll be looking at will be the ones in AASHTO. For this course, we'll be looking at two of them, which are the semi-trailer, the WB15, the semi-trailer, the WB19. And the length, these are the respective lengths. You find the WB19 is 21 meters, the WB15 is 16.67 meters. And their curb-to-curb radius is 13.67 meters, as earlier explained. And this is just showing what happens in Civil 3D. We're going to go to that quickly. Now, this is the design methodology. So we are assuming that X1, X and D are the width of the lane. So even at the bottom, D and X are the width of the lane. And the first step is what you have to do is to draw something we call the outer radius. So what you're seeing here is the outer radius, which we're naming RO. So you draw the RO, the outer radius first. Then you do something called the width offset. Now the width offset is a value in a number of manuals. There are values that you can use, and I'm going to share something with you as a quick start here in regards to the values. So I'm going to highlight the table. And what happens with the width offset is once you offset that width, you obtain something called the inner radius, which is RI. That's the inner radius I showed you in the image. That's step 3. Step 4, after we've drawn the inner radius, this way it gets a bit complicated. So we are going to try to ease the inner radius back onto the edge of the lane. And how do we do this? We use something called the easement radius. This is normally 3 to 4 times the inner radius. This is stated in a number of manuals, and we're going to use a command. We're going to use something we call a turn radius to draw this easement circle. So step 4, 5, and 6 are just showing how you draw the easement circle on both sides. Now I'm going to demonstrate this in Civil 3D because that's the most important part. So going back to Civil 3D, we have our turning radius circle here. And just to highlight, you can see this turning radius is 26 meters. This one's 25 meters. This is 25. This is 25. Now, just what I'm showing here is a junction in Japan. This is, I think, at Kishishi. And what we're having is we're showing a steep turning radius of 14 meters, and then we have another of 14.7 meters. Now earlier we showed that the curb turning radius of the design vehicles we're using is 13.67. So you can find situations in Japan they're designing the outer radius as 14 meters because they're like, we've already catered for, we've mostly catered for the biggest turning radius. And what you're finding here is there's the offset between the two turning radius. It's very good to make sure the two turning radius don't meet. It's very, very important for safety reasons. Now, we're going to look at 4 cases. One, we're going to look at a case of a radius of 13.7, a case of a radius of 30, a case of radius of 15, and a case of radius of 60. And when we try to simulate all the different vehicles, what we're going to notice is something very interesting. As the vehicles turn, as the vehicles turn, something happens in regards to the width offset. So you find 13.7, you have something along 7 meters. So as the vehicle is turning, the width of the offset is roughly around 7 meters. When you look at 15, we've increased the radius. It goes something around 6.6. When we go to 30, it's coming to around 4.9. And then we go to 60, it's coming to 3.9 meters. So what you're noticing is the higher the radius, the less the offset, the less the width offset that you need. The challenge with that is you find that this you need more right of way compared to this. And two is the different stop lines are at different areas. You find that's where the stop line would be. This is where the stop line for this would be. And this is where the stop line for this would be. And as a result, this keeps offsetting the stop line. So in Civil 3D, how would we draw this? So here I have a demonstration file that you can follow along, and this will show you, this is the exercise file we're going to be using. So earlier on, we talked about how to use Civil 3D to draw alignments. We're going to try and use alignments to try and draw how we can simulate the turning path movements. So we are going to start by drawing, we're going to start by creating an alignment. And we're going to name this NS. No, let's name it ES. Let's start with WS. We name this WS, west to southbound. Okay, so we start by drawing two fixed alignments. In this case, let's turn our snaps on. I don't really need all these labels. I'm just mainly interested in alignment. We draw another fixed snap. So we're going to start by drawing the minimum. Let's try drawing a radius of 15 here. So we have that. Actually, I may have drawn it in the wrong place. Let's target the inner lane. So let's move this here. I think that's what I like about using alignments. Alignments are quite really good and powerful. So we draw this, we draw radius less than, we select less than, and let's draw a radius of, let's start with 14. Okay, and now we're also going to draw another alignment which we're going to call an E. Let's actually, it's going to call EN, east to the north. Okay, and again the same thing. So we're going to draw a fixed line from here to there. I don't need to do the design speed for that case. And then I'm also going to draw it to this other line from here to there. And I'm going to draw radius again of let's do a radius of 14. Okay, so what you're noticing here is we're having an easement, we're having an offset distance of 2 meters, which is okay. And the beauty with this is we can always modify these as you see them fit. I'm going to just modify the alignment style to just try and get the curves to a different color. One, I don't need all these, and I just want my curves to be something along the lines of that. Okay, so that we can see the curves properly. Now, if we are to edit alignment geometry, we can easily change the radius for this case. So if we move the radius to something like 14, let's say 16, that moves inwards. And makes it easy to design that. Let's make the radius as 15. Okay. And now the goal here is to offset. Let's try offsetting by 6.5. So to offset by 6.5, type in the offset command or use any offset. I have a bar where I can just click offset here, and it's going to ask me for the offset distance, and I'm going to type in a distance of 6, radius of 15. Now go and create an offset. Just type in the offset command or just click one of the shortcuts which we have from our course in regards to automated workflows. Type in a distance of 6, and when you click offset, it's going to create this polyline. Now if you hold down Control as you're clicking, you can easily delete the lines because I don't need the lines. So just hold down Control, delete. Okay, do the same here. That, and then click there, and then hold down Control as you click, delete, hold down Control as you click, delete. Now the new radius is an offset. So if we are to just annotate in this case, you find that the new radius is 10 meters. Okay, that's okay, this is 9. So here we still have did I do 6 offset? Let me just try and make sure they're uniform both sides so that we have the same result. Let's have 15 here, and let's remove this. Let's delete. Let's do the steps again quickly. So we do an offset, that, bang, hold down Control, delete, hold down Control, delete. Again, we have the same radius. So we have equal radius. We have a radius of 9. So 3 times this radius is 27. So we're going to draw a tan circle. So you can go to the command tab, look for tan radius, or simply type in the command C and then T, and it's going to ask you what's the first point of tangency. We select this, and then the second point of tangency, in this case this, and then we type in radius of 27. Okay, and now we're going to try and trim it in 3 different directions because we want to end up with the line that's showing the swept path. So we trim this, type in trim, and then trim also this. So we have basically the initial radius, which I'm going to put in green, and then we have the easement radius. So this is the easement radius in magenta. I'm also going to draw another easement radius using the same C tan. We have that, and then we have this. Okay, so we do the same steps again. Select the 3, and then have a trim. We trim that off. We trim that off, and you're good. So we have another easement. As you can see, we've drawn that easement. Okay, so we do the same here because we're trying to draw the easement from this side to this other side. The radius is the same. We select the 3 lines, and then we try and trim them. Okay, it's mainly card work, but it kind of guides you in regards to how you draw the radiuses. Again, we select the same, have a trim, and boom, you're done. So we're now just going to match properties in regards to this, the easement circles. Okay, now what the easement circles have helped us do is try and draw what we anticipate is the turning radius, the turning movements. So I'm going to just try and use the WB15 as a demonstration. So I can now select among my design vehicles. So here we have vehicle tracking. We talk about this in the earlier lessons, detailed explanation in regards to vehicle tracking. I changed this to group by vehicle category, which I find much easier. I click US design vehicles. I select Autodesk show all the cars. Then I normally love sorting it by length because I kind of have an idea of all the vehicles by length. So roughly around 16 meters, we have this. So the semi-trailer, And we are going to try and simulate that movement. Okay, proceed, I think. So we're going to try and drive at 10 kilometers per hour at the junction, because our assumption is they'll reach the junction and then they will have a stop line. So, and then we're going to try and go very slowly, very, very slowly. Okay. Okay. So as you can see, we from our design, we have tried as much as possible to try and design a swept path analysis that's almost close. It's not that perfect. I would have maybe to push this offset further, but it kind of gives you the whole general idea. And the goal we're aiming for is, one is you're trying to have the easement radius all fitting in. Now this case we had a radius of 25, and you find our offset went to a radius of 19. So offset roughly by around 6 meters, almost similar. And then we had our easement radius as 60 either side. And you find that as you increase the radius, the more you reduce the offset and the more it fits within the swept path. So in this lesson, that's how we draw the turning radius manually. This vehicle tracking is just a confirmation, but this is a good starting point in how you draw right turning movements in regards to junction design.